So, energy conservation. So, you know that if you apply the first law for control volumes, you can write energy conservation as the heat interaction between the control volume and the surroundings minus the work interactions. Say I am putting over a dot to indicate that this rate at which the heat is interacting and the rate at which the work is interacting. The suffix x here for the work is to indicate that this is the other types of work other than the displacement work, which will not happen in the control volume. So, that will be equal to the change of total energy within the control volume with time. The rate of change of total energy E, capital E, suffix Cv is the total energy within the control volume as a function of time, plus due to mass flow rates the energy will come in and go out. So, the outgoing mass, so I will say outgoing mass is the mass which is exiting. So, m dot E into, you can say H E, its enthalpy, plus the kinetic energy plus the potential energy of the outgoing stream. So, that is the this minus what is coming in is m dot I, the enthalpy of the stream is Hi plus the velocity V I square by 2 plus the potential energy. So, this is the overall conservation of energy in the control volume. So, you can see that the rate at which heat is interacting minus the work done by the control volume to the surroundings will be equal to the rate at which the energy, the total energy capital E changes with the time, plus the mass which is leaving with its own enthalpy, kinetic energy and potential energy, minus the mass which is coming in. So, the mass flow rate which is coming in is m dot I. Similarly, the mass flow rate which is going out is m dot T into Hi, enthalpy Vi square by 2 plus G Zi, that is the potential energy. So, the mass conservation is written as the rate at which the mass within the control volume changes with time, m dm Cv by dt will be equal to the mass which is coming in, the rate of mass flow into the control volume minus m dot E, which is the rate of mass flow out of the control volume. So, this is the mass conservation here, and this is the energy conservation. So, we can say that the rate of accumulation of total energy here, okay, first term in the right hand side, plus the net efflux of total energy, that is this mass with its own energy going out divided minus the mass with its own energy coming in. This is the net flow rate of energy out of the control volume. So, by dividing this by the area of cross section, you will get a flux. So, the net F flux, the outgoing flux minus incoming flux of the total energy, this is the total energy here, is equal to the net rate of energy addition from the surroundings. It may be heat, etc., plus the rate of heat added by sources, that is within the control volume there may be some sources which can generate heat, plus the net rate of work done on the system or control volume by the surroundings. So, these are the things you can add to this basically. So, this is the statement of energy conservation. Now, in the thermodynamics point of view, it is written in a simple manner like this, but when you want to write for as a governing equation, we should involve the partial derivatives and so on. Okay. So, now let us go through one by one the terms. The total energy per unit volume, okay, the total energy per unit volume. Now, for the practical situations, the potential energies can be neglected easily. So, the neglecting the potential energy component, let us not take into account of that. So, what will be the total energy? That will be the sum of internal energy and the kinetic energy, okay, per unit volume. Please see, if you multiply this rho u by volume, so rho density into volume, that will be the mass, into specific internal energy is small u, small letter u. So, you can see that you can see rho u into V, that will be the mass into internal energy, that will be the total internal energy. So, per unit volume it will be rho u. Similarly, kinetic energy, rho V is the mass into V square by 2, that is vector the dot product of vectors V dot V by 2 rho into V. Per unit volume it is rho V dot V by 2. So, this is the total energy. Now, we can write that in a specific form per unit kg per unit mass of the mixture as E, the total energy, specific energy will be equal to U plus V square by 2. Okay. Now, U can be written as, okay, U is actually what, joule per kg. So, now we can write this per as a sum of mass fraction of each species yi into ui plus v square by 2, and U internal energy can be written by the definition of enthalpy, specific enthalpy H equal to U plus PV. So, using that I can write H as yi, that is mass fraction of each species, into its enthalpy, minus P is P by rho, pressure by density. So, V equal to 1 by rho. So, using that I can write this plus the kinetic energy V square by 2. Okay, so, this is the total energy component. So, let us see one by one the terms. So, this total energy changes within the control volume as a function of time. So, that we have to conserve. Next is energy fluxes coming in and leaving out of the control volume, okay, are due to several things. The first one is the flow of species through the control surfaces. So, several species, actually the mixture is crossing the control surface, coming into the control volume, and again through a control surface it is going out of the control volume. Okay. So, this mixture consists of several species. So, we have to actually take into account of several species. So, flow of species through the control surfaces, okay, and heat diffusion due to temperature gradient. So, this is just Fourier conduction. So, that is due to the temperature gradient, there will be thermal energy transport, that is heat conduction, that have to be taken into account. So, that is one of the energy fluxes. Okay. Then the concentration gradient at the control surfaces. Concentration gradients can prevail between the control surfaces, due to which energy can be transferred. So, that is the energy fluxes, 3 terms. Let us see how it is going to be. Now, we have to expand each of these terms. So, energy flux due to flow of species, okay, that is nothing but this. Okay. 3 terms. First one is sum of enthalpy flux of the mixture due to convection. Okay. So, there is a flow rate rho V into A. Okay. So, rho V A is the flow rate, mass flow rate. So, that is m dot, okay, into the energy which is transferred with this is H enthalpy, for example, enthalpy is transferred. So, that term. So, sum of enthalpy flux. So, this by unit area will give rho V. So, rho into V into H, the specific enthalpy, that will be the first term, that is sum of enthalpy flux of the mixture due to convection. So, something is coming in, some mass is coming in, mixture mass is coming with its enthalpy, mixture enthalpy H. So, this is the mixture enthalpy. So, some mass is coming in and some mass is going out. So, that we have to take into account. Second is sum of enthalpy fluxes of all the species due to the diffusion. So, species, this is the bulk convection, correct. The mixture is flowing with the velocity of V vector. So, that convection, bulk convection, mixture enthalpy is transported in and out through the control surfaces. That is the first term. Second term is diffusion. Individually, the species can diffuse with their own species velocity Vi diffuse. Okay. While doing so, it will carry its own enthalpy Hi. So, rho Yi, the mass fraction of that, rho I, density of the species, rho into Yi into Hi into Vi. So, this is diffusion. Due to the concentration gradient, thermal gradient and pressure gradient, etc., the diffusion velocity is calculated. Okay, predominantly we can neglect the pressure gradient, body force gradient, etc., but taking into account the ordinary diffusion, at least we can calculate the diffusion velocity Vi diff, and this into the mass of the species, rho into Yi into H. So, you have to sum up for all the species. So, this summing up is 1 I equal to 1 to n. For all the n species, this sum up is done. So, this is the total enthalpy flux due to the diffusion of the species. So, sum of enthalpy fluxes of all species due to the diffusion. The first term is the mixture enthalpy is convected by the bulk flow or the flow of the mixture itself. Second term is the individual species are diffusing at their own rate, diffusion velocity, due to which there is a enthalpy transport. Okay, so that we have to sum up for all the species. Okay, 1 to n. If there are n species. Now, then the convective fluxes of pressure and kinetic energies. So, that rho v into this, then the energy. See, for example, U has been written as H minus P by rho. So, that convection. So, this term and last term are together. So, the total energy is what? U plus V square by 2. So, that part will come as the third term. That is the convection of pressure and kinetic energies. So, these are the three terms which will contribute to the energy flux due to flow of species. Okay. So, that is the first one. Then second one, okay, here as I told you, this H is the specific enthalpy of the mixture, and the first and third terms are the bulk convection terms, mixture convection, and the second term is diffusion due to each species summed up. Okay. Now, heat flux due to conduction. Heat flux due to conduction, Fourier law. You have written right in terms of thermal conductivity and the thermal conductivity of the mixture and the temperature gradient. So, this is the term. So, where lambda is the thermal conductivity. Okay, and the gradient of temperature. So, you know that the negative sign appears because of the temperature decreasing from a particular point to another point, that same direction the heat flow will occur. So, heat flows in the direction of decreasing temperature. So, that is the flow, the heat flow depends upon the temperature gradient. So, and if thermal conductivity is higher, the heat flow rate will also be higher. So, this is the heat flux term. So, the previous term was the energy flux due to the species transport, and second one is the temperature gradient, the heat flux due to that. So, this is also a surface phenomena. So, it enters through a surface and leaves through another surface, the heat. Then the third term, the energy flux due to concentration gradients. Okay. Please understand that we have calculated the diffusion velocity, correct, for any species as the sum of the diffusion velocity due to concentration gradient and due to the thermal gradient, Soret effect. Okay. So, now this energy flux, so due to the temperature gradient, there is a diffusion of species. So, that again causes some concentration gradients, that will add energy to the control volume. So, that the reverse or the secondary effect of thermal diffusion is due to temperature gradient, there is a diffusion of species from higher temperature to the lower temperature point, that is termed as Soret effect. Now, the reverse of this, due to the Soret effect, what happens is there is a contribution for energy flux due to the concentration gradient, that is reverse effect called Dufour effect. Okay. So, that is written as RUT, and there is a summing up of this mole fraction of J into the thermal diffusion coefficient dt of ith species divided by the molecular weight of I, and Dij is the binary mass diffusivity of any two species. We are summing up for I and J's, and the diffusion velocity, difference between the ith and jth diffusion species diffusion velocity. So, this is called Dufour flux, which is the addition of energy due to the concentration gradients, the reverse effect of the reverse of the Soret effect, where the Soret effect what we saw was due to thermal temperature gradient species diffusion was happening, but here due to the concentration gradient energy flux is happening. Okay. So, but in several cases this Dufour effect is not significant. So, we need not take into account of this. Okay. So, as I told you, Ru is the universal gas constant and the MWI is the molecular mass of the ith species. Okay. So, these are the four these terms. For example, here the energy flux due to flow of species is given as this. Then the second one is the energy here in this energy flux due to concentration gradients is given here. Okay. Then heat conduction, normal heat conduction is also added. So, these are the fluxes. Okay. So, these fluxes, okay, are nothing but the energy which is transferred through the control surfaces in and out of the control volume. Okay. So, now we add up all the fluxes. Okay. Here only the diffusion is taken into account. So, the thermal diffusion, then you can see this. So, please understand the diffusive fluxes I am adding up. So, heat conduction is also a diffusion process, then the diffusion of enthalpy of each species summed up, that is one. Then Dufour effect. Dufour effect is the reverse of the Soret effect, that plus you can also add the flux due to radiative heat transfer. Okay, there are two ways to handle radiation. One, we can assume that the radiation flux, that is radiative energy per unit area, enters through the control volumes and leaves through the control volume. So, that is the net radiative energy which is transported through the control surfaces into the control volume. Okay. Now, we can also handle radiation losses or radiation heat transfer due to like using a source term, volumetric source term. Then you need not add this term here. Okay. So, the last term here is the flux due to radiative heat transfer. Okay. Like conduction, radiation also is treated as a surface phenomena. So, through the particular surface, the radiative heat transfer per unit area enters and leaves to the other surface and so on. So, the net energy which has come through the surfaces into the control volume can be calculated. On the other hand, we can also take into account of the radiative heat transfer, either may be losses or gain by the control volume. So, that predominantly flame actually loses its heat, because high temperature area flame loses its heat to the surroundings. So, I say radiation losses, that can be handled by source term. Source term means volumetric term. So, that will not come here in the fluxes. Okay. So, that is within the control volume, it will add as a sink or source. So, that will be the volumetric term that will be added. Okay. The last term representing radiative fluxes will not be included if the radiation losses are handled as a volumetric term, source term. Okay. So, that is the main point to note here. Then, so here the diffusion fluxes are summed up here like this. So, normally this term can be neglected, the Dufour term can be neglected. Okay. Now, next is, okay, now let us take the body forces. Okay. The external force per unit mass of kth species, that is represented by F k vector, okay, F suffix k vector. So, this is the term, that is the external force per unit mass of the kth species. Okay, some body force, some weight a particular species has. So, that will create some forces. So, that is the external force per unit mass of the kth species. So, this body force what we can call. So, when you have such a representation, the work interaction with the control volume due to body force of the species, okay, is written as the mass fraction of the species into body force of the species, that is the external force per unit mass into the velocity of the species. What is the velocity of the species? The bulk velocity plus its diffusion velocity. So, this is nothing but the velocity of the species k. Okay. So, now this so rho into yk will be the mass of this species into its velocity, that will be the mass flux of the species into the body force, that will be the body force term. So, each and every species has its own force, body, its weight basically body force. For example, carbon dioxide has a molecular weight of 44, so it may contribute to more external force than a hydrogen, okay. So which has the molecular weight of 2, okay. So now this term is the external work, but this normally we have to add this to the work terms basically. Similarly, the viscous terms, viscous and the pressure forces will also contribute to the work interaction Wx. So let us see this slide number 11. Here this term, this flux, okay, which is entering and leaving, which is due to the pressure and kinetic energy, the pressure and kinetic energy, that flux, okay. So rho v vector into minus p by rho plus v square by 2. So this term here, rho v vector into minus p by rho plus v square by 2. So this is the kinetic energy and pressure energy. This flux, okay, that if you take this the dot product of this with the velocity vector, okay, and combine that with the momentum equation, okay. This I am derivation is not given here, I am just explaining that due to this term you get the forces due to pressure and some viscosity, pressure and viscosity, okay. Body force is already taken into account. So work done due to pressure and the kinetic energy is derived like this. So the substantial derivative of pressure, that is d capital D p by dt, substantial derivative of pressure, plus this is the stress tensor. So tensor product of the stress tensor and the gradient of velocity. So this will give you the viscous forces. So this term is called viscous dissipation term, that is the force done by the surroundings on the control volume. Similarly, this is the pressure force term. So this is the pressure force. Okay. So now the substantial derivative d by dt is written as the partial derivative with time plus convective derivatives. Convective derivative we can write in Cartesian coordinate as u into dou by dou x plus v into dou by dou y plus w into dou by dou z, where u, v, w are the components of velocity in x, y and z direction, okay. So this is the substantial derivative. Or we can also say it is total derivative. So that total derivative of pressure will contribute to the work done by the pressure, and this viscous terms are actually captured in the stress tensor. Tensor product of that with the gradient of velocity will give you the viscous dissipation term, which is the work done due to the viscous forces, okay. So these are the force terms. So there are three force terms. Previously in this slide we saw the force, the body forces contributing to work interaction. These force terms will contribute to work interaction basically. So external force per unit volume of each species added up with its mass and its mass flux basically, which is with its mass flux, that is rho into yk into vk, that will be the mass flux of kth species, that into the body force of that will be the external force per unit volume of that unit mass of the particular this. So Fk is the external force of unit mass into the mass flux will give you the body force generated by the species K, and that summed up for all the species will contribute to the work interaction. Similarly, the viscous and pressure forces will cause work interaction. So that those terms are added here. So next is, but for incompressible reactive flow, low speed flows, only when the velocities are very high, pressure gradients are very high, then only the pressure forces, viscous forces and the body forces will be contributing to work interactions, or else the work interactions are often negligible. that you have to understand. Okay, so all the terms have been explained now. So we will try to write the overall energy equation. So energy conservation, including convective term, diffusive term, radiation fluxes. So I am adding the radiation either as a flux or a this, but in this case I am adding as a flux within the from the control surfaces it is coming into this, and the volumetric source term, this is the term, etc. But I am neglecting the Dufour effect and the work interaction terms, which I have explained how to write that, but we need not add. If you want, you can add it into this equation. For example, this is the work done due to pressure, the substantial derivative of pressure, and the viscous dissipation term. Similarly, this body force term, these three terms you can add it to the right hand side, but I have not added because for the incompressible low speed incompressible flows they are not significant. So I have neglected that. Okay. So the other terms I have added, and I am keeping the enthalpy conservation like this. So the mixture enthalpy, so the rate of change of the mixture enthalpy with time within the control volume plus the convective, this is the convective flux of the enthalpy, mixture enthalpy. The convective flux is the outgoing mass flow rate into the enthalpy of the mixture which is going out divided by the area, that minus incoming. So that F flux. So that is the second term, convective term. It is a mixture velocity, mixture enthalpy, mixture density here. So the right hand side we have the diffusion fluxes. Diffusion fluxes, first one is the Fourier conduction, and this term is the energy transport due to the diffusion species. So Vi diffusion is the diffusion velocity of each species. So rho into Yi into Vi, so that is the diffusion flux of each species into enthalpy of the species I. So that summed up for all the species, that is the energy transported due to the diffusion of the species, and here the energy transported due to radiation, Q radiation through the control volume. So I have taken the flux term, and this is the source term. If there is any source, that can be handled here. In some cases it may not be used at all. Okay. So the mixture enthalpy H is calculated using the standard specific enthalpy of species Hi or absolute enthalpy. Okay, Hi like this. Okay. See, for example, Hi at any temperature T will be the heat of formation at the reference temperature of 298 Kelvin plus the sensible enthalpy, which will take the temperature from Tref to T. So that the energy added due to that increase in temperature. So this you have to find for all the species, and this should be in mass basis, so that the mixture enthalpy can be calculated as the sum of product of mass fraction of each species into its specific enthalpy, mass based specific enthalpy. Okay. So this you know, so that is the conservation, total conservation. So you need the information about the species enthalpy of each species plus the mixture enthalpy. So you have to calculate the thermal conductivity of the mixture. Then you can see that here you are calculating the density of the mixture and the enthalpy. Then when you calculate the diffusion velocity, you need the binary diffusion coefficient of all the species taken into, or the overall diffusion coefficient of a particular species going into mixture and so on. Okay. Similarly, heat transport due to the radiation can also be counted here. So this is the conservation of energy. You can see that the additional terms, normally if you take say heat transfer applications, you do not have this particular term, okay, basically, but now the enthalpy transport due to the species diffusion is also one of the important thing, and also the enthalpy when you calculate it is just Cp into T in the heat transfer application, but you can see that enthalpy formation etc. comes here due to the reactive nature of the system. Okay, now in terms of temperature, okay, when you want to write in terms of temperature, we have to use definition here like this. Okay, dH is equal to Cp dt plus Hi del Yi. Okay, this is definition of the change in the specific enthalpy of the mixture will be the mixture specific heat into dt. So this itself Cp of the mixture itself will be a function of temperature. So, this you have to integrate basically, plus integral Hi into del Yi. Okay. So, this is the second term. So, which I have to add. So, this you have to use. Then we have used species conservation equation multiplied by Hi and summed up all the species. If you take species conservation equation, okay, for each species, that multiply that by Hi overall, then add up for all the species, then you will get the this and this combined together, you can write this equation. Okay. Here you see that the rho mixture density Cp of the mixture into dou by dou T of temperature plus rho Cp into V dot gradient of temperature. This is the convective term here. So, now enthalpy is expanded and the energy equation is written in terms of temperature. So, now that will be equal to the gradient of the conduction flux plus this. So, you can see I am using the species conservation equation multiplied by Hi and summed up of all the species. So, that will give this term. The source term of each species is the rate at which the species is consumed or produced. So, omega dot I triple dash. So, that is the volumetric source term, that into Hi. So, I am multiplying the species conservation equation by the Hi and summing up. So, that summed up term is the term here, that comes out as a source term here. Similarly, the flux term remains like this, but here instead of writing enthalpy, I am writing Cpi into gradient of temperature, Cpi of each species and gradient of temperature. Previously, we wrote Hi. Instead of Hi, I am now writing as Cpi into gradient of temperature plus the flux due to the radiation and any source term. Okay. This is the volumetric source term I have written here. So, these are the things. This actually in the previous slide it was written as this is same as this. Okay. So, now you can see that you get the volumetric source term basically, which is non-linear in nature. So, this is one of the important additions. So, these two are the terms which is important for the reactive flows. The energy transport due to diffusion of species. Okay. Similarly, the energy generated due to the volumetric reactions of each species. So, these two terms are important for the reactive flows. Other terms you can see in general heat transfer applications. Okay. So, the entire derivation is not given here, but to derive from this enthalpy based energy conservation, we have to use this definition dH equal to Cp dt plus Hi into gradient of Yi. Okay. Then species conservation equation for each species multiplied by Hi, its own enthalpy, specific enthalpy, and summed up for all the species. That will give rise to this equation, which is written in terms of temperature. So, that is the primitive variable we want in the terms of temperature. So, when you write the equation in this term, then you can directly solve for the temperature. Okay. So, now please see that for energy equation, you need individual species. Now, you can see that Cpi is involved. So, specific heat at constant pressure for individual species is required. Then Hi, standard or absolute enthalpies of all the species is required. Okay. These have to be calculated as a function of temperature basically. Then specific heat of the mixture at constant pressure Cp. Okay. This has to be calculated as a function of concentrations as well as temperature, both. Okay. Now, rho is calculated using the equation of state. So, this is the consolidated energy equation. Please understand, in this we have neglected the work interactions due to pressure force, viscous dissipation and the body forces. So, this have been neglected here.